Okay, so far we've learned much more about the motor cortex and how that initiates movement. So, let's suppose we have our motor cortex right here. And we have, let's say, our thalamus. We'll just say medulla's right here, and our spinal cord. So this was the spinalcortical tract that Katrina was talking about. So let me just make this into the middle. So let's suppose, we'll just say this is the right side. We have a pathway going from the motor cortex to the thalamus that's called the internal capsule. So I'll just abbreviate it IC. And then, there's much more two tracks, the lateral and the anterior. We know the lateral kind of desiccates at the medulla level, and the anterior actually comes down and desiccates towards in the spinal cord. And they come and control our muscles. So the anterior corticospinal tract, ANTERIOR, controls much more. So this is the one that desiccates at the level of the spinal cord. It controls our axial muscles. And the lateral one, which desiccates at the medulla, so lateral, controls much more our limbs. A good way to think about it is A, axial, L, limbs. And it's LM, just an alphabet. So the lateral desiccates at the medulla. So, so far this is what we've learned. And so you can kind of think of this as just executing a function. Our brain will tell let's suppose these axons ended in our hands. This will just tell our hands to contract or to move or whatever, right? So now we want to look at the bigger picture. What's going to regulate this, or what's going to initiate it much more, our preconscious efforts. And that's where the basal ganglia comes into play. The basal ganglia actually has a lot of functions. It's associated with coordinating movements, procedural learning, habits, cognitive and emotional functionings. But for right now, let's look at it in terms of movement. Just assume that it's helpful in initiating movements. Initiate, I'm not sure if I spelled that right, movements. So this is the step before the actual motor cortex, before the brain sends our muscles to contract, right? And it's important to do this because suppose there's someone, so now let's suppose there's a hand, and they're trying to pick up, let's say, a ball, right? There's so many ways, someone can grab a ball. They can go straight forward and grab the ball, or, they can wiggle their hand around and get the ball by this. So let's suppose you're playing a baseball game. It's obvious you want the most speed, and it's going to be, logical for the hand to directly, go the shortest distance to get the ball. It doesn't want to waver and get the ball. So we need our brain, or we need to, preconsciously tell our brain, this is the route we want to take. We want to take route A. We don't want to take route B. So what we have to do is that we have to activate route A, and we want to inhibit route B. So that's where the basal ganglia is going to come into play. Before we start talking about the circuitry, let's talk about much more of the anatomy. Okay, I'll just draw it down here. So if we're looking at the brain from this angle right there, the basal ganglia is kind of a weird structure. It's kind of almost shaped like a mini brain, kind of like a C-shaped structure. Kind of like starts right there and kind of loops around back here. But in the slideshow which Katrina showed us, there's actually a coronal section, so it's what's shown when the brain is cut in the middle. So what she shows you is a structure that kind of resembles this thing right here. So I'll give it my best to draw the brain. The corpus corpus callosum, come back, go like that. You know, for anatomy, don't worry about it, just worry about the terms or what, you know, parts that you have to know. So we'll just say, we'll draw the lateral ventricles, thalamus, and stuff. Okay. So the first thing that you have to know is something called the caudate. So C-A-U-D-A-T-E. So that's the first part of the basal ganglia. The second part is the putamen. P-U-T-A-M-E-N. Next is the globus pallidus. The globus pallidus is actually, let me just move this. It's actually split into two structures. There is the internal, which I'll say is I, and there's the external globus pallidus. So GPI stands for globus pallidus internal, and GPE stands for external. There's two other structures. One is a substantia nigra. Substantia nigra, as well as the subthalamic nuclei. Subthalamic nuclei. I know this is not a good picture, but if you look in the slides, you know, the main things that you have to know is we have the caudate, the putamen, the two sections of the globus pallidus, the substantia nigra, and the subthalamic nuclei. And so one of the first things that you'll see is we actually group the caudate and putamen together. And we actually call that the striatum. S-T-R-I-A-T-U-M. So striatum is just collectively referring to both the caudate and the putamen. So it's still part of the basal ganglia. Okay. So now let's talk much more about the circuitry. So like I said in the baseball example, you know, we're trying to activate or excite the pathway that we want to get. We want to reach the ball fast as possible, and we want to inhibit pretty much every other movements which aren't going to be as efficient. So by that logic, we need two pathways, right? We need something that activates it, that activates behaviors that we want to perform, and we want a pathway that inhibits, I-N-H-I-B, inhibits pathways that we don't want. And for this, I want you to think of activating as a direct pathway and inhibiting as the indirect pathway. Okay, so let's focus much more on the direct pathway first. But before we focus on the pathway, I want to talk about a concept, or just some neurotransmitters, what they do, and the concept of disinhibition. So we'll come back to the basal ganglia. Let's just get into some neurons and stuff. So let's suppose we have a neuron, and we have another neuron right here. Let's suppose we have another neuron right there. Okay, so the two neurotransmitters that we'll be looking at is glutamate and GABA. So typically glutamate is an excitatory. And we'll refer to as GABA as inhibitory. So let's see what that means. We'll just number these 1, 2, and 3. So if this first neuron in series has glutamate, what that means is this is going to excite the one that it's next to. So we'll just say, we'll just give this plus to refer to that it's releasing an excitatory neurotransmitter, which is going to allow the neuron that it's connected to release whatever transmitter that it needs to release. So this is going to excite this guy right here. Okay. So, this is typically going to release glutamate because it's excitatory. Now, let's not worry about this guy. Let's worry about neuron number 2. If this releases GABA, if the second neuron is releasing GABA, it's going to inhibit the neuron that this is connected to. So when the second neuron is releasing GABA, neuron number 3 isn't going to release a transmitter that it needs to release. So effectively, neuron number 2, which is releasing GABA, is inhibiting the neuron that it's connected to. So that's how glutamate and GABA work. Now, one phenomenon is the concept of disinhibition. You can think of this when you have 2 inhibitory neurons next to one another. What that is going to lead to is excitation. Let's see. Excitation. I-O-N. Okay. So for example, let's suppose we have a neuron right here connected to another neuron, which is connected to another neuron. Okay, so we'll just say this is A, this is B, and this is C. So let's not worry about A right now. Let's worry about B. So if we say B has GABA, that means we'll just say this is minus because GABA is inhibitory. It's inhibiting C, which B is connected to. So when B is turned on, when it is inhibiting C, C isn't releasing anything, right? So C is being inhibited. But what happens when we inhibit what is inhibiting C? So let's suppose now A is also releasing GABA. So A is now inhibiting B, but B used to inhibit C. But if we inhibit B, it's not going to be inhibiting C anymore. Let's just go over that one more time. So let's not worry about A. B right now is inhibiting C when it's turned on, right? So B is turned on and it's inhibiting C. So we see no transmitters being released from C. But now we're inhibiting B. A inhibits B. So if we're inhibiting something, it's going to start releasing neurotransmitters. Let's put that in layman's term. Let's suppose, B is kind of like a kidnapper. Don't know how to draw a kidnapper. We'll just say this guy has a ski mask. Can't see anything. So we have a kidnapper which has kidnapped someone. Think of this as B and think of this as C. C can't run. It can't, transmit anything. But let's suppose, A is kind of like a police officer or something. We'll just, draw him with a gun. It is a really bad police officer. Now, if the police officer is going to inhibit B, or inhibit the kidnapper, C can now effectively run. It can get away, because whatever used to inhibit C is now being inhibited by the police officer. So this is kind of parallel to what the concept of disinhibition. If it's hard to think about it much more in depth, but just think in your mind, whenever you see the concept of 2 inhibitory neurons together, it's typically going to excite whatever the second neuron is connected to. Oops, hope everyone can see that. Okay. So now that we covered that, let's look at the actual circuitry of the basal ganglia. If you understand that concept, the concept of disinhibition, now it's pretty straightforward. So now we're going to put together the anatomy, the striatum, which consists of the caudate and the putamen, the 2 segments of the globus pallidus, as well as the let's not worry about the substantia nigra for right now, and the subthalamic nuclei. So let's just see how those things work. So let's start with the direct pathway first. The basal ganglia is going to get its information from the cortex, because that's ultimately where our decision-making things, specifically the motor cortex, specifically the prefrontal motor cortex. So we'll just say cortex right here. I'm referring to the motor cortex, but we'll just say cortex. It has a connection directly to the striatum. So, we'll just say the striatum is right here. striatum. So the connection is positive. Like I said, when it's a plus, that means it's sending glutamate. So the cortex is exciting the striatum. So we'll just say glutamate. The striatum is then connected to, just put this right here, specifically the GPI, so Globus Pallidus internal one. But this is actually going to be a negative connection. So this is going to be GABA, or it's going to be an inhibition. So the cortex is sending glutamate to the striatum, exciting it. But when the striatum gets excited, it's actually going to inhibit the Globus Pallidus internal section. Now, the Globus Pallidus is also going to send GABA, so an inhibitory signal, to the thalamus. Just as a review, we know pretty much everything goes through the thalamus. It's the relay station of the brain. Does this seem very familiar? When you have two inhibitory neurons next to one another, we know that now whatever it's connected to, it's going to be excited. Concept of disinhibition. So the thalamus is actually connected to, we'll just say, the motor cortex. So then, the corticospinal tract comes into play, which we've talked about. The actual execution of the events. So pretty much everything prior is us trying to unconsciously regulate which behaviors we want to perform. And so this concept right here, this is glutamate, so this is positive. Glutamate. M-A-T-E. Okay, so just as a review, the cortex is going to excite the striatum, which is going to inhibit the Globus Pallidus, which is already inhibiting the thalamus. But if you're inhibiting something that's inhibiting the thalamus, you're going to excite it. You're going to really excite it, and then it's eventually going to excite the motor cortex. So ultimately, at the end, you're activating the motor cortex. So we'll refer to this as a direct pathway. We're selecting for behaviors that we want to perform. This would be like grabbing the baseball, the example that we talked about, just directly, without, flailing our arms everywhere. So I'll just kind of put this in a dashed box. Okay, so now let's talk about the indirect pathways, or how our brain really selects against the behaviors that we don't want to perform, or behaviors that aren't as effective, such as, flailing our arms to get the baseball. So, it's very similar. The cortex is going to, still activate or send glutamate or excite the striatum. But now this is where the other parts of the basal ganglia come into play. From there, the striatum is actually going to inhibit, so I'll just say minus. So this is going to be GABA. It's going to inhibit the Globus Pallidus external segment. Okay? The Globus Pallidus external segment is then going to also inhibit, so GABA, the subthalamic nuclei. So, the same thing that we talked about. When we have two inhibition, it's going to lead to disinhibition. So whatever the subthalamic nuclei is connected to, it's actually going to be activated because we're inhibiting what it's really connected to. So, the same logic applies. So the subthalamic nuclei is actually connected back with the Globus Pallidus internal segment, so it kind of forms like a loop. That's why it's referred to as the indirect pathway. So, you know, this will be much more positive, and this would be glutamate, Glutamate. Okay, and you know, if we're exciting this, but once we're exciting the internal segment, we know that it's inhibiting the thalamus. So if we're inhibiting the thalamus, we're ultimately going to be inhibiting the motor cortex. So this guy right here is really referred to as the indirect pathway. Let's just go over the indirect pathway just one last time. So we know ultimately the indirect pathway is going to decrease motor cortex activity because we're selecting against the behaviors that we don't want to perform. So the cortex is going to be activated, is going to activate this striatum or excite it. In that sense, when that's excited, it's going to inhibit the GPE, which is going to inhibit the subthalamic nuclei. But because it's getting inhibited by something that's it's attached to, so we know that the globus pallidus internal is going to be excited because it's just disinhibition when you see two inhibitions together. So once this is excited, this is going to send, you know, GABA, or it's going to inhibit the thalamus, which is ultimately going to, if you're decreasing the thalamus activity, you're going to decrease the motor cortex activity. So this is pretty much how the indirect pathway and the direct pathway are working.